Okay, what we want to talk about here is something called a Fourier series. So a Fourier series is pretty interesting. It's used to represent periodic functions, and basically Fourier had a theorem. And what his theorem says is that any periodic function of any shape, as long as it's periodic, can be represented as a series of sine and cosine waves. And those sine and cosine waves are integer multiples of fundamental frequencies that are weighted via amplitude. Now, what's a periodic function? A periodic function is any function that repeats at a given consistent time, t, the period. And you will see in some spots in these notes, this is referred to as t with a subscript 0. But oftentimes, capital T stands as period, and it's a constant number, and it has units of seconds. Now the frequency, the fundamental frequency of any periodic wave is 1 over t, where t is the period of the wave. When sine and cosine functions are used as what's called basis functions. So what are basis functions? Basis functions, and this is kind of a mathematical thing that you'll see later, so this is not necessarily something that you need to commit to memory at this point. But basis functions tend to be orthogonal functions, and they're like a family of functions. And so sines and cosines are one option for basis functions. In a Fourier series, when you use sines and cosines, it's referred to as the trigonometric Fourier series. The other option in the Fourier series that's beyond the scope of this class is an exponential Fourier series. So in that case, you would use, excuse me, the exponent in the series with a different kind of coefficient. So for the trigonometric Fourier series, which is the one we're going to talk about, basically we have three components. One is a sub 0, which is a constant term. And then there is a sum from 1 to infinity of weighted cosine functions. So a sub n is referred to as the coefficient. N is an integer between 1 and infinity. And basically inside the cosine function is n omega naught t for the argument. Omega naught is the fundamental frequency in radians per second. So it would be 2 pi over the period. So basically this guy expands into a sum. And then you have the same thing with the sine function. You have the sine of n omega naught t. Omega naught, once again, is a constant. It's equal to 2 pi over the period. It has units of radians per second. N is an integer going from 1 to infinity, and so this would expand into a sum. A sub n and b sub n are coefficients. And what they give you an idea of is for a given value of n, so let's take n equals 2. This frequency would be 2 omega naught. So the cosine function would be the cosine of 2 omega naught t. So as you've seen in previous videos, that's just a cosine function with a given frequency. What a sub 2, the coefficient when n is equal to 2, would represent is it represents how much of that frequency is contained in that given waveform. B sub n is the same thing, only it's multiplying the sine function. And then a sub 0 is like a DC term. So in a given signal, you'll often have a bunch of different frequencies, and you'll have like a DC offset or a DC term. So what the Fourier series does, let me go back, sorry. What the Fourier series does is it gives you the DC term, and then it gives you some weighted cosines and some weighted sines. And notice that since n is an integer and omega naught is a constant fundamental frequency, we're basically getting integer multiples of the fundamental frequency. For n greater than 1, those are referred to as harmonics, higher frequency harmonics. When n is equal to 1, then you have that's the fundamental frequency. It's worth pointing out that a sub n and b sub n for any value of n can and often are, can be and often are 0. So it's not unusual not to have terms for n equals 1, 2, 3, 4, 5, and so on. It's sometimes common to have n only being odd. It's sometimes common to have n only being even. Sometimes all of the sine functions have zero coefficient. Sometimes all of the cosine functions have zero coefficient. Obviously, you've got to have some terms or you won't create a waveform. Now, how do you get the a sub n's? You get the a sub n's by modeling what the periodic function looks like mathematically. And so there are some formulas that allow you to get a sub n and b sub n for a given waveform. We're not going to go over those because they involve concepts of orthogonal functions and integration, and this class does not require calculus as a prerequisite. But for those of you who have had calculus, there is a Word document that I will upload as a part of this unit. And if you want to explore this further, you may read the Word document to explore how we get a sub n and b sub n, these coefficients for a given waveform. Okay, each term in the sum is going to have a unique coefficient, as we already said this, and a frequency that's an integer multiple of the fundamental frequency. The period of repetition of the periodic function is given by a t sub 0, there's a 0, which is equal to 2 pi over omega 0, and the first constant represents the DC offset of the waveform. So because it's a sum of distinct sinusoids, the power spectrum is going to consist of discrete lines, a lot like those shown in the example shown associated with figure 5, which was the one we looked at in the previous video. Okay, here is an example. So let's go back again to this equation. In reality, we can never sum infinite number of frequencies. So at some point, we terminate the sum and this equal sign gets replaced with an approximately equal sign. Let's say we were trying to actually synthesize a square wave. We actually could not have an infinite number of sources with different frequencies present to make that wave. So we have to terminate this sum somewhere. As a general rule, most Fourier series tend to converge. In other words, you get diminishing returns with more than about 5 or 6 terms. Not all, but most. Certainly by the time you get 10 terms in your series, then you pretty much are reproducing the waveform fairly accurately. So let me go back to the figure. Here is an example. The blue line is the square wave, and that's what we're trying to reproduce by adding a bunch of harmonic sinusoids together. So in this first part, the top figure, all we've plotted here is the sinusoid with the same fundamental frequency. So how would we get the fundamental frequency here? If this were labeled, we would find the time it takes to get from here to here. In other words, the time it takes for this to go through one full cycle. And I'm talking about the blue line here. So following the square wave from here to here would be a full period. Whatever that time is, that's the period in seconds. And so the fundamental frequency from that in radians per second is 2 pi over that time. All right, so this is just the fundamental frequency sinusoid plotted. And you can see it goes through 0 at the same time, it peaks at the same time, but it has a sinusoidal shape, not a square shape. If we now add the next non-zero term in the series, we see that we now have something that has a little faster rise time. It's got some squiggles, but it's getting flatter at the top and at the bottom, and this transition is getting steeper. And then with 3 terms, you see something similar. With 4 terms, you see something similar. So a couple of things that start to show up as you go to higher and higher terms. You have, instead of a flat segment here at the max and min, you have some oscillation, and that's referred to as ripple. It's also referred to as the Fresnel effect. Some of you may have had a physics class where you looked at the effect of passing light through a pinhole or around an edge, and you note that you see a fringe pattern. So nature doesn't like sharp transitions. So to actually construct a circuit that gives you a perfect square wave is something nature really hates. So what nature is going to try to give you is it's going to give you this ringing or this ripple effect. The more components you put in the series, the more ripples you have. Also notice that we get a little bit of what's referred to as overshoot. Notice how this first and last peak are a little bit taller than the ones in the middle. If you were to plot this with a bunch of terms, you'd see a taller peak, and then you'd see it decay, and then you'd see it come back up. So it's symmetric about the middle for the square wave. So you do get some overshoot and you get some ripple, and that's one of the engineering trade-offs about how much of that you can actually tolerate, because the faster you try to go, meaning more and more frequency components, so as you add higher and higher frequency components, you'll approach this vertical edge, but you'll also have a more significant problem with ripple. Okay, so here are the A's, B's, and C's for various different waveforms. So we have a series of pulses, and here this is only shown for t equals 0, but the t equals 0 and higher, but it also exists for t less than 0. So we have a series of pulses, we have a square wave, a triangle wave, a sawtooth wave, a rectified wave, cosine wave. So these are just different waveforms. This is a table that I just pulled out of a source. In this case, I believe the author is plotting this versus F, the fundamental frequency. So you'll notice here on this first one, there is a DC term. You'll notice, and that's plotted at a frequency of 0. So what's being plotted here is an amplitude spectrum, okay? And so the first one, and I actually believe it's an absolute value, maybe. I think they've made everything positive. But I'm actually not sure about that. So you can see that here are the coefficients. And in this case, all of the cosine terms are 0. Actually, you know what? I think that's sine terms. Let's go back. I think I kept my equation consistent. Yes, the B's are the sine terms. The A's are the cosine terms. So like in this first one, here is the amplitude of your pulse, and t is the period of your pulse. And then this little tiny pulse length is k. So if those were specified, you would know that your coefficients for the nth term would be 2a over n pi. I think that's actually supposed to be, oh, okay, and then d is k over t. So they put these in terms of d. So your DC term would be whatever your amplitude is times this parameter d, which is the pulse width over the period. And then your first term would be 2a over pi times the sine of pi d. And then the third term would be 2a over, or the second term would be 2a over 2 pi, and so on. And you notice all the terms are present here. You notice we come down, and then we have a little bit coming back up. If you were to extend this, you would have this pattern repeat in the frequency domain. But basically what these lines are telling you is they're telling you there is a lot of fundamental frequency energy present in this pulse stream. There's also a lot of DC energy. Let's contrast that with a square wave. You notice the square wave has no DC. Why is that? If you look at the average of this wave, it averages to 0. So it actually doesn't have a DC term. Notice there's a lot of amplitude present in the fundamental frequency. So what that means is that's this one. Okay. And then notice in the second term, which is actually 3 times the fundamental frequency, because in this particular wave, it turns out all even harmonics are 0. We get a smaller portion of the wave there, and then we get even smaller. And so this dies away very quickly. So you can see on this one, really by the third term, we've represented a lot of energy present in that wave. And so that's kind of verified. You can see here, by this term, we're getting pretty close to duplicating that waveform. So it kind of depends. How many terms you need depends on kind of the shape of the waveform. For the triangle wave, notice that we have the fundamental frequency Once again, all the even harmonics are 0. And notice that this dies off as 1 over n squared. So the higher the n, the lower the magnitude of the contribution of that sinusoidal term. So we're dying off pretty fast here. Really by 3 terms, we have virtually no terms left, or no power left in this little tick mark. So so basically that's how the amplitude spectrum looks in the different waveforms here. And these are the equations that would give you the coefficients of the sines and cosines associated with each one of these types of waveforms. So before we go any further, because we have covered a lot of stuff, I wanted to provide this slide so that you have a review of sort of the terminology that we've been using. So T sub 0, once again, is the period of repetition of a periodic wave in seconds. F sub 0 is the fundamental frequency in hertz, and it's equal to 1 over T sub 0. Omega sub 0 is the fundamental frequency in radians per second, and I need to fix this slide because this should actually be over F sub 0. So what we're going to do is we're actually going to fix that right now. So let's put in the slash, and then we'll go right back to slideshow mode. Okay, so going back to our slideshow. Oh, no, what am I doing? I was right to begin with. I'm sorry. I'm clearly, this has been kind of difficult to do, so let me go back and refix that. Sorry. It would be 2 pi over T naught. So let me put a T here, and that's basically then also equal to 2 pi f. So go ahead and do that. Okay, so now we got it. So, oops. I'm going to tell you, I don't love PowerPoints, some of the things they do on the, see this, that shouldn't do that. There we go. Really? Okay. Just going to put an F there. And you know that it's F sub 0, and I'll fix that later before I republish it. I don't know why it's doing that. Like I said, PowerPoint does that sometimes. All right, so going back to slideshow mode. Periodic function, once again, another term, is a function that repeats after one period. Harmonics or waveforms that occur at frequencies that are integer multiples of the fundamental frequency. And let me say the fundamental frequency does not actually have to be present in the Fourier series. So it's possible to have a Fourier series that includes the integer multiples, but doesn't include the actual fundamental itself. It can have a coefficient of 0. That is very unusual. You would almost never see that, but it's mathematically not impossible. All right, so I want to give a couple of new definitions because we're going to talk in a future lecture about even and odd functions. So an even function is a function that can be reflected around the vertical axis. And mathematically what that means is f of t is equal to f of minus t. An odd function is a function that is first reflected and then inverted around the vertical axis. So f of t is minus f of minus t. Even functions can have a DC offset and still be even. Odd functions cannot, so you will never see a DC term in an odd function. An even function can be a sum of even functions. An odd function can be a sum of odd functions. If you sum even and odd functions together, it is neither even nor odd. So one of the things about the Fourier series is that if you have an even function, you will have only cosine functions and possibly a constant in your Fourier series. If you have an odd function, you will have only sine terms in the Fourier series. So in other words, you can never build an even function out of odd functions, and you can never build an odd function out of even functions. So that's just kind of a basic fundamental rule. It seemed like there was another important point I was going to make, and it's escaped me. Let's see. Also super important, you don't have to be even or odd. You can be neither. So there are going to be some slides that come up that kind of go back over that. Okay, so here's an example. This is the Fourier series of a sawtooth waveform. So this formula comes from some mathematics that's beyond the scope of the course. So what I want you to understand is not necessarily, what we're doing with how we got the formula, but what we want to do with it. So basically this does have, you can look at this function and tell, it's not centered around the axis, it's not centered around the horizontal axis, so it's not going to be, it's going to have a DC offset. And you also notice that in this case, this particular function is neither even nor odd. So we have a constant term, and then we have a series of sinusoids. Because if we were to shift it, it would be an odd function consisting only of sinusoids. Anyway, you don't have to get any of that. All you have to get is that we have this formula, and that if we do this sum with n being 1 to infinity, and so our constant is 1 over pi times n, so the first coefficient would be 1 over pi, the second coefficient would be 1 over 2 pi, third coefficient 1 over 3 pi, and then inside the sine function you would have 2 pi t, 4 pi t, 6 pi t, and so on. So you could write this out longhand using several terms. And then if you were to plot an amplitude spectrum, the first term of the amplitude spectrum would occur at frequency of 0, and that would be 1/2. And then the next term would be minus 1 over pi, and the term after that would be minus 1 over 2 pi, and so on. That would be the amplitude. And it would occur at frequencies of 2 pi, 4 pi, 6 pi radians per second, respectively. So using the amplitude terms, what I did was I used MATLAB to determine the amplitude of the first 10 coefficients. And I did that without the DC term. And then I set up a new array to add the DC term in, and I used a bar plot. On the bar plot in MATLAB, you can set the line thickness, so I set it to be 5% of the spacing between points so that it looks like lines instead of boxes. So let me show you that. So here's where I took n as 1 through 10, and the amplitude only is minus 1 over n pi. And so I calculated the amplitude for 10 terms, and then I set up a new array called frequency that consisted first of 0, so that I got the DC term, and then of all the terms that followed in the matrix that went from 1 to 10. So here I'm going from 0 to 10. And then I added the 1/2 term right here. I added that to the amplitude terms, and then I plotted the bar plot. So you can see right here, we have a 0.5 amplitude at 0, and then I have a minus at n equals 0, and then I have a minus 0.3183 at n equals 1. So I'm plotting this versus n. If I wanted to plot it versus time, then I would have to figure out what, versus frequency, then I would need to take my n and multiply it by 2 pi. So instead of 1, this would be 2 pi, 4 pi, 6 pi, 8 pi. And I couldn't figure out right offhand in the plot command how to get that to use the symbol pi instead of the number. So I didn't do that. I didn't plot it versus omega. I plotted it versus n. So plotting it versus n, since the whole thing is omega, n is basically frequency. So this is 2 pi, and so the fundamental is f sub 0, which is 1, or 2 pi radians per second. So anyway, this is just a plot of the frequency spectrum or amplitude spectrum And notice that I went ahead and plotted the negative values, which is fine. That's why I called it frequency spectrum and not amplitude spectrum. If I'd called it amplitude spectrum, I'd be plotting the magnitude of this. I didn't want to do that because it was important to me to show you that some of these can actually be negative. All right, in the next lecture, we'll discuss even and odd functions more thoroughly.